Problem 10 is very simple. You're given an h of n and you're expected to find the DTFT, which is defined as you simply have to substitute this expression here and solve it. We've done a similar example in the lecture notes, and it's also there in the book, I think, the very same impulse response. So solving this, if I remember correctly, you're supposed to get something like 1 over 1 minus 1 over 3 e to the negative j omega. I'm not sure about this, but that's what I remember. So that's A. Finding the magnitude and phase. Again, you're free to decompose this into a cosine and a sine. That should give you 1 over 1 minus 1/3 cosine omega minus j sine omega, which gives us a real and imaginary part of 1 minus 1/3 cosine omega plus j times 1/3 sine omega. We know that the magnitude is going to be the magnitude of the numerator, which is 1 divided by the magnitude of the denominator, which is square root of the real part times the imaginary part, which is 1 minus 1/3 cosine omega squared plus 1/3 sine omega squared, which is 1 over square root. This should be 1 plus 1 over 9. So the cosine square and the sine square omega would combine, and here you get negative 2 over 3 cosine omega, and this is just 1. So you're left with 1 over square root 1 plus 1 over 9 is 10 over 9 minus 2/3 cosine omega. The angle for h e to the j omega is going to be the angle of the numerator minus the angle of the denominator. The angle of the numerator is 0. It's 1 times e to the j is 0. So it's 0 minus the angle of the denominator is tan inverse imaginary part over real part, 1/3 sine omega over 1 minus 1/3 cosine omega. There is a very similar example in the lecture notes. You can go back and look at it. Now C asks you to find a difference equation for y. Now what he's telling you is that this expression that you have for h is also equal to the output Fourier transform over the input Fourier transform, and your hint is to cross multiply it. So that means it's x e to the j omega equals y e to the j omega minus 1/3 y e to the j omega e to the negative j omega. simply take the inverse dtft of both sides. You should get x of n equals y of n minus 1/3. So it's y e to the j omega multiplied by e to the negative j omega, which should be y of n minus 1. Right? The time shift comes out at like this. So the difference equation, just rearrange in terms of y. So give me something like yn equals what? And that's like a causal equation, right? Because you've written yn in terms of yn minus 1. For d, we are expecting an anti-causal version, so you simply need to rearrange it so that you are getting y of, the first step would be to get y of this particular term, y of n minus 1, in terms of yn and xn. Then you would change n to n plus 1 so that your equation looks like yn equals something of yn plus 1 plus something of x of n plus 1. So this is an anti-causal equation for the same system. And the question is the result from part D stable? Maybe by looking at the coefficients you may be able to make a guess, or well, think about it. When you get the answer and then make an observation, what do you think? Is it blowing up? Does it look like it'll become infinite or something? That's how you would do E.